Welcome to the fourth uh, video lecture in our Class 18 series of video lectures. This is our final lecture. We kind of looked at reduction of carbonyl compounds to give alcohols. We also looked at Grignard reactions followed by aqueous acidic workup to give alcohols. So now we ask the question, how about oxidations? Well, we can certainly convert an alcohol to a carbonyl compound, removing two hydrogens, one hydrogen from the carbon to which that hydroxyl group, alcohol group, is bonded, and the other hydrogen from the hydroxyl group itself. Sometimes we symbolize oxidation as a small O in brackets. Let's look at chromium trioxide. One way that we write chromium trioxide is exactly this, CrO3. Another form of chromium trioxide that we could use is something called potassium dichromate, so K2Cr2O7. Here's a nice little Lewis structure of the dichromate anion, dianion actually, with the corresponding potassium cations. Each chromium has a total of how many bonds to oxygen? Well, if we counted them up, we would count 6 bonds. This is okay for transition metal. Transition metals like to have, sometimes they shuttle between 16 and 18 electrons. It's an 18 electron rule because we have 5 d orbitals, each of which can accommodate 2 electrons. With these 6 bonds, you might say that each chromium has, let's see, 2, 4, 6, 8, 10, 12 electrons, but we say that when we have a metal and something is electronegative as oxygen bonded to it, we say however many bonds we have to oxygen is our oxidation state. So we say that that is chromium 6. Sometimes we use a Roman numeral to symbolize that oxidation state. If we throw this in water, we can break it up. Oftentimes we will add H2SO4 so that we'll have the protonated form of this potassium chromate salt. And so how does it work? I won't actually hold students responsible for a mechanism for oxidation, but I thought it would be nice if they knew how potassium chromate oxidations work. You could put either chromium trioxide or potassium dichromate in acidic water. Usually we use sulfuric acid. We create this chromic acid with chromium 6. If we've got an alcohol in the mix, like let's say we have isopropyl alcohol, we could exchange one of these groups for our isopropoxide group. So we would lose a total of H2 and an oxygen. So we lose water, we exchange one of these OHs for our, alkoxide part of our alcohol. And then something interesting happens. We do this series of 4 double-headed arrows. So what are we doing here? Well, it looks like we're giving electrons back to chromium, and we're plucking this hydrogen off of our carbon, and we're forming a carbon-oxygen bond. So here we go. We're at acetone, and if we follow the arrows correctly, now we have a chromium with just a double bond to oxygen and 2 other bonds to OHs, and so it's chromium in the +4 oxidation state. If our isopropanol got oxidized, well, our chromium gained electrons, 2 electrons in fact, and was reduced. So chromium trioxide will oxidize secondary alcohols to ketones. Under aqueous conditions, chromium trioxide or potassium dichromate will over-oxidize primary alcohols to carboxylic acids. And so here we go, ethanol, chromium trioxide in the presence of water. Yes, we'll go to the acetaldehyde, but we don't stop there. Aldehydes can form things called hydrates, We'll talk about this a lot more in the second semester, but then we can repeat the process, remove another H2, and all of a sudden we have acetic acid as our major product. And so if you're looking for acetaldehyde, you have to use an alternative oxidation method, and we'll talk about that. This is an interesting series. Of course, your liver does this to alcohol when you have a glass of wine or drink. It will try to oxidize that alcohol all the way up to acetic acid to expel it. If you drink a little too much, your liver might be overwhelmed, and the cytochromes that it uses to oxidize your organic molecules may get saturated, and you may get stuck at acetaldehyde, and that's not good because this will cause liver cirrhosis and other problems. So interesting side note there. What is the alternative that we can use to stop at the aldehyde so we don't over-oxidize to carboxylic acid if we're not looking for a carboxylic acid? And the answer to that is to prevent over-oxidation of primary alcohols, that is, to stop at the aldehyde, chemists use something called pyridinium chlorochromate. That's it's a big word, right? So we abbreviate it as PCC in the absence of water. If you threw in water, it would behave just like chromium trioxide or the potassium dichromate. It would over-oxidize your primary alcohol all the way to a carboxylic acid. What's nice about PCC is it dissolves in most organic polar A product solvents like dichloromethane, so we don't have to worry about having water present. So if we take this isobutyl alcohol and we add PCC and there's no water present, so we're in anhydrous dichloromethane, we stop at the aldehyde. It will not further oxidize ketones, so they get stuck. And like I said, if you throw in water, it behaves just like chromium trioxide or potassium dichromate in water. It will over-oxidize your isobutyl alcohol to a carboxylic acid. So that pretty much does it for this fourth and final lecture video for our Class 18 series of lecture videos. Good luck with the questions.